I want to tell you about the last piece of a puzzle I spent my entire working life circling without ever managing to place it correctly myself, and about work happening now, decades after my death, that suggests physicists may finally be closing in on where it actually fits. The secret in question is unification. The question of whether the four fundamental forces that govern everything in the universe, gravity, electromagnetism, and the strong and weak nuclear forces, are ultimately expressions of a single, deeper underlying framework rather than four genuinely separate phenomena that simply happen to coexist. I want to walk you through why physicists have spent well over a century believing this unification must exist, why three of the four forces have already been successfully unified, while the fourth has resisted every serious attempt, and what I think the most promising recent work suggests about why gravity specifically has proven so stubborn. The history of this pursuit is, in a real sense, the history of physics itself, progressively discovering that phenomena which once appeared completely unrelated are actually the same underlying force, viewed from different angles or under different conditions. I want to walk through this history briefly because I think it explains why physicists remain so confident that a final unification exists, waiting to be found even after decades of frustration. In the specific case of gravity, Isaac Newton in the 17th century achieved what was for his era an extraordinary unification, demonstrating that the same force responsible for an apple falling to the ground here on Earth also governs the motion of the moon around the Earth and the planets around the sun. A single law of universal gravitation, rather than separate, unrelated rules for terrestrial and celestial motion, which had been the prevailing assumption for essentially the entire history of astronomy before Newton's work. This was genuinely revolutionary, establishing the principle that phenomena appearing completely distinct at first glance might actually be governed by exactly the same underlying physical law. The next major unification came from James Clerk Maxwell in the 1860s, who demonstrated that electricity and magnetism, phenomena that had been studied largely separately for most of the preceding centuries, are actually two aspects of a single underlying force, electromagnetism, described by a unified set of equations that remain to this day essentially unchanged from Maxwell's original formulation. Maxwell's equations went further still, revealing that light itself is simply a particular kind of electromagnetic wave, unifying the study of optics with the study of electricity and magnetism in a single theoretical framework, a genuinely stunning result that transformed how physicists understood an enormous range of previously separate phenomena. I spent much of my own working life immersed in a third unification, one that occurred through the 20th century's development of quantum field theory, particularly through work completed largely after my own death in the 1960s and 70s, showing that electromagnetism and the weak nuclear force, the force responsible for certain kinds of radioactive decay, are themselves unified into a single framework called the electroweak force, distinct and separate only at the relatively low energies characteristic of everyday physics, but merging into one single underlying force at sufficiently high energies. The kind of energies that existed throughout the universe in the earliest fractions of a second following the Big Bang. This pattern, repeated across 3 centuries of physics, is why physicists have long suspected that all 4 fundamental forces, including the strong nuclear force that binds quarks together inside protons and neutrons, and ultimately gravity itself, might similarly unify into a single, more fundamental framework at sufficiently extreme energies, even though those energies are so far beyond anything achievable by current or foreseeable particle accelerators, that direct experimental confirmation of a full unification remains, for now, entirely out of reach. I want to be specific about where this unification project currently stands, because I think the honest picture is considerably more interesting and more nuanced than a simple statement that physicists haven't yet succeeded. The standard model of particle physics, the theoretical framework I discussed in an earlier conversation about CERN's search for physics beyond it, already achieves a substantial and genuinely impressive partial unification. It successfully describes electromagnetism, the weak nuclear force, and the strong nuclear force within a single, mathematically consistent framework, using the language of quantum field theory, and this framework has been tested and confirmed with extraordinary precision across an enormous range of experiments, culminating most recently in the 2012 discovery of the Higgs boson. What the standard model conspicuously fails to include, despite this genuine and hard-won partial unification, is gravity. And this isn't simply an oversight or an unfinished piece of bookkeeping. Gravity, as described by Einstein's general relativity, the framework I spent years of my own career working directly within, particularly in my 1939 work with Hartland Snyder on gravitational collapse, is built on a mathematical foundation genuinely incompatible with the quantum field theory framework that successfully describes the other three forces. General relativity treats space-time itself as a smooth, continuous, dynamically curving geometric structure responding to the presence of mass and energy. Quantum field theory, by contrast, is built around discrete quanta, probabilistic behavior, and a background space-time that in its standard formulations is simply assumed to already exist as a fixed stage on which quantum fields operate, rather than being itself a dynamical quantum mechanical entity. Attempting to naively combine these two frameworks, applying the mathematical techniques of quantum field theory directly to gravity, the way physicists successfully applied them to the other three forces, produces mathematical infinities that the theory has no consistent way to handle. The same fundamental incompatibility I discussed in our earlier conversation about what actually happens inside a black hole singularity. This is a specific problem that a genuine, complete theory of everything would need to solve, finding a mathematical framework capable of describing gravity in a manner fully consistent with quantum mechanics, ideally unifying it with the already successful standard model description of the other three forces within a single, coherent theoretical structure. I want to walk through some of the most serious approaches physicists have pursued toward this goal, because I think understanding the genuine difficulty of the problem requires appreciating just how many different mathematically sophisticated strategies talented physicists have attempted across decades of dedicated effort without yet achieving a fully successful, experimentally confirmed result. String theory represents perhaps the most extensively developed approach, built on the proposal that the fundamental constituents of reality aren't point particles, the way the standard model treats quarks and electrons, but extraordinarily tiny, one-dimensional vibrating strings with different vibrational patterns of these strings corresponding to what we observe as different fundamental particles. String theory has the genuine mathematical virtue of naturally incorporating a particle with exactly the properties gravity's force-carrying particle, the hypothetical graviton, would need to have, emerging directly from the theory's mathematical structure rather than needing to be separately inserted, which many physicists working on the theory consider a strong hint that string theory is pointing towards something genuinely correct. But string theory, in most of its currently developed forms, requires the existence of additional spatial dimensions beyond the three we directly experience, typically 6 or 7 additional dimensions depending on the specific version of the theory, compactified down to a scale far too small for any current or foreseeable experiment to directly detect. And the theory has so far struggled to produce specific, uniquely testable predictions that would allow experimentalists to confirm or rule it out definitively, a limitation that has generated real and, I think, largely legitimate criticism from physicists who worry the theory has become more mathematical structure than testable physics. Loop quantum gravity represents a genuinely different approach, one that doesn't attempt to unify gravity with the other forces within a single overarching framework, the way string theory does, but instead focuses specifically on quantizing gravity itself, treating space-time not as a smooth continuum, but as being built at the smallest scales from discrete granular units, somewhat analogous to how ordinary matter, viewed closely enough, resolves into discrete atoms rather than a smooth, continuous substance. This approach has produced some genuinely interesting mathematical results, including specific quantitative predictions about black hole entropy that connect meaningfully to the black hole information paradox I discussed in an earlier conversation. But it has, like string theory, struggled to produce experimentally testable predictions within reach of any currently achievable experiment. I want to describe one more recent line of research specifically, published in 2025 by physicists Mikko Partanen and Jukka Tulkki at Aalto University in Finland, because I think it represents a genuinely interesting and importantly different approach to this same underlying problem, one worth understanding on its own terms, rather than simply as another entry in a long list of unsuccessful attempts. Their approach, published in the journal Reports on Progress in Physics, attempts something more mathematically conservative than string theory's dramatic proposal of extra dimensions and vibrating strings. Rather than proposing an entirely new fundamental substrate for reality, their work develops a quantum field theory formulation of gravity constructed to remain directly compatible with the mathematical structure of the standard model, treating the gravitational field using techniques closely analogous to how quantum field theory already successfully describes the other three forces, working in what's called a perturbative framework, calculating gravity's quantum field on a flat background spacetime, with the familiar curved spacetime of general relativity emerging as the expectation value of that underlying quantum gravitational field, rather than being assumed as a separate classical starting point, the way most other approaches to this problem have generally proceeded. I want to be honest and careful about how to characterize this work appropriately, in the same spirit of intellectual caution I've tried to maintain throughout every one of these conversations. This represents a genuinely serious, peer-reviewed piece of theoretical physics, published in a respected journal, attempting a mathematically rigorous approach to an extraordinarily difficult problem. It has not been experimentally confirmed, and given the extraordinary difficulty of directly testing any theory of quantum gravity, the energies required to directly probe quantum gravitational effects sit vastly beyond anything any conceivable particle accelerator could achieve. It likely won't be confirmed or ruled out through direct experimental tests for a considerable time, if such direct experimental confirmation ever becomes practically achievable at all. I find myself thinking about this entire research program and the specific difficulty gravity has posed to every serious unification attempt, in relation to my own experience with the 1939 gravitational collapse work Snyder and I completed together, we understood, even then, that general relativity's prediction of a genuine singularity at the center of a sufficiently collapsed star represented the theory reaching the edge of its own validity, a place where some additional physics, not yet developed, would eventually need to take over. I didn't know in 1939 what that additional physics would look like, only that some deeper framework, incorporating quantum effects in a way general relativity alone couldn't accommodate, would eventually be required. The search for a genuine theory of everything, I think, represents exactly this same recognition, generalized far beyond the specific context of collapsing stars. General relativity and quantum mechanics, both extraordinarily successful within their own respective domains, cannot both be complete and correct as currently formulated, because they make fundamentally incompatible assumptions about the basic structure of reality. And resolving that incompatibility requires a genuinely new framework that neither theory on its own currently provides. I want to address directly why I think physicists remain confident, despite decades of frustration, that such a unification genuinely exists waiting to be discovered, rather than concluding that gravity might simply be a fundamentally different kind of phenomenon, incapable of ever being reconciled with quantum mechanics in the way the other three forces have already been reconciled with each other. The strongest argument, I think, comes directly from the black hole physics I discussed in an earlier conversation regarding the information paradox. We already have strong theoretical evidence through the holographic principle and the related mathematical work on replica wormholes that gravity and quantum mechanics can be made consistent with each other, at least within specific mathematically idealized contexts. This doesn't yet constitute a complete, generally applicable theory of quantum gravity, but it demonstrates, with real mathematical rigor rather than mere hope, that the fundamental incompatibility between these two frameworks is not some permanent, unbridgeable feature of reality, but rather a genuine solvable problem in our current theoretical understanding. One that specific careful mathematical work has already shown can be resolved, at least in certain limited but genuinely instructive cases. I want to close by reflecting on why I find this ongoing search, despite decades of accumulated frustration and repeated false starts, genuinely one of the most exciting unresolved questions in all of physics, rather than a discouraging tale of persistent failure. Every one of the unification stories I've described throughout human history, Newton's unification of terrestrial and celestial gravity, Maxwell's unification of electricity, magnetism, and light, the 20th century's unification of electromagnetism with the weak nuclear force, required, in each case, decades or even centuries of dedicated theoretical and experimental work, often including long periods where the eventual unification seemed genuinely out of reach, before the pieces finally came together into a framework simple, elegant, and experimentally confirmed enough that it became, in retrospect, difficult to imagine physics ever having been understood any other way. I think the search for a genuine theory of everything, uniting gravity with the quantum mechanical description of the other three forces, occupies exactly this same historical position now. A problem physicists have every good reason to believe has a real discoverable solution, based on the repeated historical pattern of apparently separate phenomena eventually revealing themselves to be unified expressions of a single, deeper, underlying framework, even though the specific mathematical form that final unification will actually take remains, as of now, genuinely unknown. contested among several serious competing approaches, and likely to require considerably more decades of careful, patient theoretical work, building on efforts like the recent work from Aalto University and the many other serious research programs pursuing this same fundamental question before physics finally arrives at whatever this last, most stubborn secret of the universe actually turns out to be